So in order to follow this proof, we need to have a good picture of some of the properties of numbers as shown in this diagram. Numbers can be either real or complex. Recall that a complex number has an imaginary part to it. Now, every real number is either rational or irrational. A rational number can be expressed as the ratio of two integers, and an irrational number is a real number that can't be expressed as the ratio of two integers. So the theorem that we're going to prove that if r is a positive real number and r is irrational, then the square root of r is also irrational. So the hypothesis consists of two parts. The first part says that r is a positive real number, and the second part says that r is irrational. And the hypothesis is the and of these two statements. But the conclusion is that the square root of r is irrational. So we're going to use a proof by contrapositive. So we start by assuming the negation of the conclusion. So the negation of the conclusion is that the square root of r is not irrational. And we have to show that under that assumption, the hypothesis is false. Now, since the hypothesis consists of two parts, we actually have to only show that one of the two parts is violated. So we're going to take H1 and use that as one of the assumptions, and we'll show then that H2 has to be violated. So the two assumptions are that the square root of r is not irrational, and that r is a positive real number, and we'll use these two assumptions to show that r is not irrational. And you can check by assigning variables to each of the individual components of these statements that the two statements are actually, in fact, logically equivalent. So now we know from our assumptions that square root is not irrational. But what we'd like to be able to say is that the square root of r is rational. Because if we can do that, then we can express the square root of r as a ratio of two integers. And this gives us a convenient algebraic expression for the square root of r that we can then plug into other things. However, if we look at our map of numbers here, the only thing that we know from the first assumption that the square root of r is not irrational is that the square root of r doesn't sit in here. We haven't ruled out the fact that it's complex. And that's where the second assumption comes into play. So if r is a positive real number, then we know that the square root of r is a real number. So we have two facts here. The first fact, that r is not irrational. The second fact is that the square root of r is real. So we know the square root of r has to be among the real numbers, but it's not irrational. And given that, we can conclude now that the square root of r is in fact a rational number. This allows us to express the square root of r as the ratio of two integers. Since we want to make a statement about r, because we have to show that r is not irrational, the logical next step is to square both sides of this equation. The left-hand side becomes r, and the right-hand side becomes a squared over b squared. Since a and b are both integers, a squared and b squared are also both integers, and we've managed to express r as a ratio of two integers. So we conclude that r is rational, and therefore we can conclude that r is not irrational. So looking back at the choice of proof technique, a direct proof would have required working directly with the fact that r is irrational. Knowing that a number can't be expressed as the ratio of two integers is not as useful in reasoning about properties of that number. On the other hand, the contrapositive proof that we used here allowed us to reason that the square root of r is rational, and we were able to express the square root of r as the ratio of two integers and use that expression to reason then about the properties of r.